Hi guys, today we're going to be talking about conformance control using nanoparticles. Our advisors are Dr. Carson Thompson, Dr. Richard Hughes. They've been kind of helping us with this project. I am Spencer King.
I'm Shelby Hedgepeth.
Adam Ollie.
Rosales.
Some background of our project is going to be talking about primary recovery and secondary recovery. In primary recovery, you only obtain about 25 to 30% of what was originally in the ground, at which point you need a secondary energy drive to force more oil out. The most popular in the industry today is water flooding. It allows you to increase your ultimate recovery by about 5%. The way water flooding works is that we send water down an injection well, and it acts as a piston, pushing out the less dense oil. However, once the water reaches the production well, it's then reached breakthrough point, as we call it, and at breakthrough point, it's no longer economically feasible due to high disposal costs. The way we combat this is using conformance control. Conformance control allows us to produce more oil and less water by means of increasing our sweep efficiency in the reservoir. The reasons we should care about this is that it's costing the industry about $40 billion per year just in water disposal costs due to the fact that once it reaches breakthrough point, it is now 75% of the overall production.
Okay, so traditionally what the industry has been implementing so far is the use of polymer flooding or weak gel system. For our senior project, what we've been thinking of using is the weak gel system. This system usually uses a lower concentration of polymers with crosslinkers together. However, specifically for our project, what we were thinking of doing is encapsulating the crosslinkers. Because what the weak gel system, one of the disadvantages of the weak gel system is the gelation usually happens near the wellbore. Therefore, if we'll be able to encapsulate the crosslinkers, we'll be able to control when the gelation time happens. And by that, we'll be able to get deep inside the reservoir and block those paths of least resistance. And therefore, whenever we do secondary water flooding, the water will push the oil that are in the thief zones, which will eventually increase our recovery factor.
So nanoparticles have been used in the oil industry since about the 1970s. However, there are a few things hindering their widespread use. The first is the behavior of nanoparticles inside the reservoir is not fully researched and fully known. There's four major avenues of behavior inside the reservoir itself. You have transport, which is how deep the particles actually penetrate. There's deposition, which is how much the particles are actually left inside the reservoir. You have dispersion, which is what the concentration is, the particles at different points in the reservoir. Then you have recovery, which is how much of the particles you actually recover through your production well. Now, one of the major reasons why nanoparticles, there's not a lot known about them is because there's not enough field data. There's not been enough research done to actually understand much about them. And also, most commercial simulators can't handle their small particle size. So with that in mind, companies aren't willing to invest more in their research, and this kind of propagates into companies not being willing to invest in low economic return for the particles. Our simulator that we're going to be using to study these particles is called Streamline-Based Nanoparticle Flooding Simulator, or NPSL for short. It was developed by the grad students at ULL and LSU, and it's still being improved, but it's at a point now where we can have it and start to figure out how it works. We're going to be studying the timed release of encapsulated nanoparticles throughout the reservoir, and we're going to be trying to use the simulator to gather data about these particles and then compare it to other valid sources like UT-gel and Eclipse, and then should our end results be the same for similar reservoir conditions and similar parameters, we will know that our reservoir or our simulator is useful and valid. Now, it provides feedback in three ways. It provides 3D real-time visualization as the simulator works. Peer review, which is an application that is attached, takes the data and makes it visual in a 3D way and analyzes that data. And then it also exports data, the hard data, in table format in Excel. And our simulator is broken into three major pieces, packages. There's the backbone, which is the executable file, which you attach all the large files like reservoir conditions and injection conditions, production conditions. And then you have the Excel interface, which is for the more changeable, lighter conditions like injection rate and concentration of particles. And then you have pair view, which is, like I said before, for visualization and analytics.
So throughout the semester and next semester, we're focusing on these things here. Basically, we've already set up the simulator in PFT. Now we're learning how to use the simulator, what we can change in it. Next, we're going to validate the simulator by comparing it to the other simulators Spencer spoke of earlier. That's going to be the first part. The second part is going to be adjusting the variables in the simulator to better perform our nanoparticles in recovery, such as the strength of encapsulation or the method of injection. Once we produce the results that we think are the best, we're going to compare them to the other simulators and see which one is more efficient and more cost effective. For our project to be a success, we're going to measure it on this scale here. It's going to be step 1 of validation, step 2, compare the results to others, and step 3, changes in the oil industry. We spoke to our advisors throughout the semester. They gave us the okay to use the HPAM particles and to use the encapsulated crosslinker system. They've also told us what we should manipulate in the simulator to maybe give us different results. And they've introduced us to the simulator designers, which are John Blair's and Ben Wing.
The project management aspect of our project has been broken up into a twofold situation. For the first is the use of Asana for our day-to-day interactions and keeping up with our to-do list. As you can see here, we can assign different topics to individual people. We can also communicate via comments. We can attach files to individual comments. And once a topic is done, you can check it off. You can also assign due dates. Some challenges we've encountered along the way have been mostly due to communication issues. It took a lot longer than we expected to obtain the simulator. The way we've overcome this is really improving our efficiency in the way we communicate to our advisors and to ourselves and what we expect of each other. It's not only allowed for interpersonal improvement, but as well as the overall project efficiency improvement. The Gantt chart is the other part of our project management. It's a visual representation of our overall timeline, and everything we have left remaining to do will be in the coming semester, and it's broken up into about how long we think it will take, and it can be changed based on if it moves or needs to be adjusted. The responsibilities amongst ourselves, I have the management plan, which involves updating Asana, keeping us on track of our to-do list, keeping us on track of our timeline as well. Spencer's in charge of our project secretarial things, and that includes keeping track of everything we're doing in a written form. That way we can integrate it into such things as like our written project proposal, written lit review. Adam's in charge of the scope of our project, which really involves the chemistry and the technological aspects. Corey's involved in project marketing. That involves interfacing with the industry officials, as well as coming up with budgets, because at the end of next semester, we're going to need to know if it's economically feasible to really use these nanoparticles in the industry today.
Thanks, guys.
That's all we have.
Thank you.
Thank you.
Money.